let's get going. So, anybody who's leaving for spring break? Like going completely away? All right. I apologize directly to you guys. You're going to have to do 2 daily problems just because of the amount of time we missed. I am very sorry. I dislike giving problems over break because it gives you time to recharge. But thanks to the bomb threat and the other cancellation that we have, we kind of have to get through it. Now, after looking through your daily problems, everybody could do the acid-base chemistry neutralization reaction. They could do that one fairly well. But a lot of people were having an issue with daily problem number 19 where we were looking at a redox reaction. And what we're going to do, we're going to go through and we're going to work that problem out right now. And then we'll return back to the ideal gas law stuff that we were doing. All right, so the problem is asking us how many electrons are transferred when we have a certain amount of solid iron and a given molarity, which I completely forgot to write in here, of 2.750 molar copper nitrate. Now, even though you have a volume and you have a molarity, you still can figure out moles from this, right? So what kind of problem is this? Yeah?
Limiting reagent?
Yeah, it's a limiting reagent problem. So what we have to do, we have to calculate amounts of each substance that we have and see what the total amount of products is that we can get from each of them. And then we're going to check out and see what is the least amount of electrons that we can get out of this process, and therefore identify the limiting reagent. All right, so let's start by converting that grams of solid iron to moles of solid iron. Or we can take a step back further, and what should we do to start with? Where do we even go? What do you always need?
Balanced equation.
Always got to get that balanced equation. All right, what's reacting? Iron, solid. We also have what else? Copper nitrate. Aqueous. We then have been told we're going to form iron 3 nitrate, which means we're going to be left over with solid copper. Now this is a redox reaction. How do we know?
Because you're given two amounts for each.
Right, that would be a limiting reagent problem though.
Oh.
So how do we know we have a redox? What's changing? Yeah.
There's a transfer of electrons.
There's a transfer of electrons. Oxidation states are changing. Let's isolate the species where the oxidation states are changing, and then we can see how many electrons are flowing. So let's start with iron. On the left side, iron is in what oxidation state? Kind of a trick question. 0. Whenever an element is completely by itself, it has an oxidation state of 0. On the right side, even though those nitrates are there, those nitrates are just there as counterions. They're not really important to the chemistry, right? Their oxidation state isn't changing. What do we need to do with this top reaction before we continue, though? Got to balance it. All right? What number should go here? 2. Yep. There's a 2 there. There's got to be a 2 here. What about in front of the copper nitrate? Copper 2 nitrate?
3.
3. Yep. There are 3 coppers on the left side, 3 coppers on the right. Okay, let's return back to our half reaction. So we have 2 irons in a 0 state. What oxidation state are they going to? Or what charge do they have? +3. You know that because each nitrate has a what charge? -1. Since there are 3 of them, that totals to be a +3 charge. All right, now which side do the electrons need to go on, the left or the right?
The right.
The right. Why? Charges are equal on both sides. We need to conserve charge on both sides. How many electrons do we need? 6. We know that because each iron goes from an iron 0 to a +3, showing that each of them needs to give off 3 electrons. Since there are 2 of them, it's a total of 6. All right, now let's look at the change of the oxidation states of copper. What's copper on the right side? What's its oxidation state? 0. What about on the left? Yep, a 2 plus charge. Which side do the electrons need to go on, the left or the right?
The left.
The left. How many of them do we need? Need a total of 6. All right, so now for every 3 moles of copper, we know we transfer 6 moles of electrons. For every 2 moles of iron, we transfer 6 moles of electrons. Now let's figure out the total number of electrons that we could transfer with both amounts of our iron and our copper nitrate. So let's start with just iron. So we're going to start with that mass 5.884 grams of iron. We need to do some sort of manipulation to it. What unit has to go in this denominator? Yep, grams of iron. What's going to go up top? Yep, moles of iron. For every 1 mole of iron, how many grams are there? 55.845, right? Oh, I'm good. All right. We're not done though, right? We're only in moles of electron. They're moles of iron, excuse me. I just gave away the next step. What unit goes in the denominator?
Mole.
Moles of iron, moles of Fe. What unit's going to go up top?
Electron.
Yep, moles of electrons. Where do we get the digits that go in here?
From the balanced half reaction.
Yep, from the balanced half reaction. So this half reaction here. So what number is going to go up top? 6, just because that's how many moles of electrons we have. How many moles of iron?
2.
So for every 2 moles of iron, we produce 6 moles of electrons. Have we, yeah,
I have a question. Going back to the half reaction, you
Yeah.
said Fe has a -1 charge? Or a minus charge?
no, nitrate has a -1 charge.
Oh, okay, never mind.
So the iron itself on the left is a 0 charge. On the right, it accommodates a positive charge. Metals typically always have a positive charge. So, yeah. Okay, so have we answered the question yet? What's the last step we need to do? Or what do we got to try and figure out? Number of actual electrons. So what unit's going to go in this denominator then? Moles of electrons, what's going to go up top? Yep, electrons, and you gave me the correct unit or digit. 6.022 times 10 to the 23rd goes up top. 1 goes in the bottom. When you multiply that all the way through, I get an answer of 1.903 times 10 to the 23rd electrons. Is that our answer? Maybe. We don't know yet. We got to figure out how many moles or how many electrons we can produce from that copper nitrate. So we have one more step that we need to do. All right. So what's molarity equal to again?
Moles over liters.
Moles over liters, yep. Jeez. Don't know my own strength. All right. Molarity is equal to moles over liters. What are we going to try and solve for? We've got to try and get moles. So we should manipulate this equation around in order to solve for moles. Moles is going to be equal to what? Yep, molarity times liters. Now we have the values that were initially suggested in our problem. The molarity was 2.750 molar. What was the volume that we had? I think it was 105.0 milliliters. Are we good to keep it this way? No. What do we got to convert that milliliters to?
Liters.
Yeah. For every 1 liter, how many milliliters are there?
1,000.
Yes, 1,000. When you multiply that all the way through, I get 0.28875 moles of copper 2 plus. Now you might be saying, wait, isn't that copper 2 nitrate? The nitrate's not really involved in the chemistry, right? The electrons aren't really being transferred. That nitrate just exists as a counter ion. So it's not so important to the chemistry. All right, so what are we going to do with this value that we just found out?
Figure out how many electrons.
Yeah, I heard somebody say convert to moles of electrons. At least I thought I did. Or the voices in my head tell me so. All right, for every, what digit's going to go in the denominator?
3.
3, where'd you get that from?
The balanced half.
Yep, that balanced half reaction, the one that involves copper. What's going to go up top? 6. Decided to jump the gun. What unit's going to go in the denominator?
1 mole.
Yep, 1 mole of electrons. Yep, 6.022 times 10 to the 23rd electrons. When you multiply that all the way through, the value I get is 3.478 times 10 to the 23rd electrons. So which one is our answer? Why do you say that? Yeah, there's less that's been produced. This is a limiting reagent problem. We only have so much of our reactants. We're going to get the least amount of whatever you put in, right? Okay, so that's how you go about doing that problem. I really suggest to go over that once or twice. There will be a question very similar to this on the exam. All right, so where did we leave off last time? We're at the ideal gas law, right? And we took those simple gas laws and we combined them into one grand unified equation of state. And I claimed that you didn't need to waste your time memorizing those simple gas laws. Well, let's look at the daily problem that you had to turn in today. Try and see how that's true. So, we had our daily problem where the Joker runs in a room, he takes this, he spikes it down, gas goes everywhere. Do you live or do you not?
You die.
Who says you live? Or who calculated you'll live? No one did? Man, you guys are a bunch of pessimists. Who? No one thought you would live? All right. Let's check it out. So, what we have is the Joker dashes in a room. And he spikes. $5,250.00 milliliter vial of Joker toxin. Trademarked. All right. The initial pressure of the vial is at a whopping 863,200 kilopascals. And the pressure of the room is a little less than 1 atmosphere, 755 torr. And then if the volume of the room is 600 liters, what are your chances of survival? Also, should you call the Batman? Yeah, the Batman. Not just Batman. Oh, question mark. So you guys know a simple gas law that can get us to a reasonable answer. The crummy part is you're getting two pressures and two volumes. What you have to try and do is come up with a rationale if you'll live or you won't live. That way the next time it happens, you'll be prepared. Yeah. Okay. So what simple gas law can we use? Could use Boyle's law. What is Boyle's law? P1, V1 is equal to P2, V2. What does that assume? At constant temperature and amount of moles, right? Well, I'm going to show you, you don't have to utilize the simple gas law. What you can do is go through the ideal gas law to solve this problem. What is the ideal gas law again?
PV equals nRT.
Yep, nRT. And what we're going to do, we're going to say we have state 1. Put little subscript 1s by all the variables. And then we're going to have a second state. PV equals nRT. A state 2. So we said we have constant temperature and we have constant number of moles, right? They're not going to change, assuming we don't inhale any of the deadly Joker toxin and assuming the temperature doesn't change very much when you crack that vial. So what can we say about the variables? What's N1 going to be equal to? Should be equal to N2, right? What about T1? Yeah, it equals T2. That means what we have is a scenario like this. P1, V1 is equal to nRT, which is equal to P2, V2. All this is just a constant. And if we set these two equations equal to one another, we can get rid of the constant. And we arrive exactly at Boyle's law. Whoa, man. All right. So that's the equation we're going to utilize. So there are two different ways you can try and figure this out if you'll survive or not. One is to say you have a room of this size, calculate the pressure. What you'll find is the pressure would probably squish everybody in the room. The other way you could do it is you could calculate the volume that that gas would occupy at approximately 1 atmosphere. And see, compare that gas volume to the volume of the size of the room. So let's take that second option. All right. So what we're going to be solving for then is V2. V2 is going to be equal to what? P1, V1.
Over P2.
Yep, over P2. All right. We need to make sure we're in common units though. The pressure of the vial is that extremely large value of kilopascals. We want to convert that over to what unit? Let's go to ATM because ATMs are a little bit more intuitive in a way than kilopascals. All right, kilopascals is going to go on the bottom. Let's just convert to pascals. For every 1 kilopascal, how many pascals do we have?
1.01325.
Oh, I meant just kilopascals to pascals.
Oh.
Yeah, 1,000. I already wrote it in for you, sorry. Now let's go from pascals to atmospheres. For every 1 atmosphere, how many pascals do we have? 101.325. When you multiply that all the way through, I result with an answer of 8,519 ATM. Okay. B1, we need to get the volume into what unit? Yeah, let's get it to liters. So we have 5,250.00 milliliters. Just got to convert that over to liters. There are 1,000 milliliters for every 1 liter, as we all know and are probably extremely bored of. This results in an answer of 5.2500 liters. We have 1 variable left. Let's convert our last pressure, P2. Let's convert that to ATM. Our pressure was 755 torr. We want to try and convert that to atmospheres. How many torr are there per atmosphere? 760 for every 1 ATM. When you multiply that all the way through, I get 0.993 ATM. Okay. Now all we have to do is plug and chug and compare our volume that we calculate to the actual volume of the room. All right, so V2 is equal to P1, V1 over P2. Let's plug in our variables, 8,519 ATM times 5.2500 liters, all divided by the pressure of the room, 0.993 ATM. When you multiply that all the way through, you end up getting something 4.504 times 10 to the 8th liters. That volume is much greater than that of the room. What are your chances of survival? It ain't good. Not good. Call Batman. The Batman, excuse me. I don't know how you do that. Does Yuri have a bat signal? Yeah.
Could we have done it by pressure inside of the vial and pressure in the room?
Yeah, you could do it the exact same way. What did you calculate your pressure out to be? You remember?
More in the vial than the room?
Yeah, it was really large still, right? It was something along the lines of, I think, like 8 ATM? Oh, 7 ATM. So that's the pressure of 7 atmospheres pushing down on everyone. Chances are, as soon as the Joker spikes that vial, he will die instantaneously from the pressure change. Or at least everybody's eardrums will be punctured. Woo! All right, so let's see an example of this. We've already seen a couple. What I wanted to do was get a peep and put it in this container and watch as we torture the peep. But I'm not a sick individual. Also, I don't want to eat a bunch of peeps over break, so I didn't want to do that. They're the worst candy on the planet. That is not true.
Not true.
So instead, we're going to do something a little different. What I have here is some shaving cream. And there's a little bit of gas that's released inside of the shaving cream that makes it foam up, right? So we're going to squirt a little bit of this guy in there. Maybe. I can get this to work. Oh, I've got to pull the cap off. Let's put a little bit in there.
Just a little.
Yeah. There we go. All right, so there's a little bit of gas that's trapped in that foam there. What do you think is going to happen as we pull a vacuum on this guy? It'll expand? Why do you say that?
No, it'll get.
It'll expand? Why do you say it'll expand? Right. Pressure and volume are inversely proportional to one another, right? If you take away some of the pressure that's exerted on this foam, it should expand, right? The volume should grow. So let's activate the pump and see what happens. There we go. Oh, God! All right.
Something's happening.
Now, what do you think's going to happen when we take this cap off?
Oh.
Woo! Flattens it all out. It actually evacuates all of the gas on the inside of the foam, and it kind of squishes it. So that's like stale shaving cream. All right. So we've seen the ideal gas law in its most simple state. Can we try to change things up a bit and get a little more information out of this? Well, actually, yes, we can. There's a relationship between density and molar mass that's involved in the ideal gas law. So, what we're going to talk about next is density and molar mass of a gas. My rhymes are fat, yo. All right. The number of molecules, or excuse me, the number of moles N is given by N. It's given by what? What do you do normally to convert, or how do you figure out moles? Yeah, you need grams, right? And what do you do with those grams? You have grams of, let's say, chemical X. What unit would go down here? Grams of X. What unit would go up top? Moles of X. What is this?
Molecular.
It's a molecular weight. What we can say then is have a generic equation where we have our mass, and it's going to be divided by our molecular weight. That's a fancy M. So this will be our molar mass. And this is going to be the mass of our gas. What if we take that and we sub that in to the ideal gas law? What kind of relationships will we get then? Can we get anything that resembles density? Well, let's see. All the physicists in the room are happy about all the equations I'm using. They get to live out their dreams while the bio people are sad. Sub into the ideal gas equation. The ideal gas law is what again? P.
V equals.
Yup. Okay, let's sub in what we just determined. PV is equal to the mass of our gas divided by the molecular weight, or the molecular mass, times R times T. Okay. I said that we would relate this to density. What's density equal to again?
Mass over volume.
Yeah, mass over volume. So how about we manipulate this equation around in order to solve for mass over volume or density? So what we're going to do, we're going to move the variables around. And what you'll find is if you have the pressure times the molecular weight divided by the ideal gas constant times temperature, that's equivalent to mass divided by volume, or a density. You're going to need to utilize that equation or that relationship on your next daily problem. All right. So we have 2 more topics to cover in Chapter 5, and then you'll be free to do what you wish over break, including my daily problems, sorry. All right, what we have to talk about next is this idea of partial pressures. Partial pressures. So far we only talked about one gas. What happens when we have a mixture of gases? How does that change the game? Well, Dalton, who we talked about before, came up with this law of partial pressures. And what he said was the total pressure, or the pressure that all of the gases collectively exert, is the sum of the pressure of each individual component in our system. This makes intuitive sense, right? If I have one hand that can push down with 1 Newton, hopefully I can push down more than 1 Newton because I've been going to the gym, but maybe that's all I can get out of this hand. If I go to push with my other arm, assuming it's of equal strength, how many newtons am I going to be pushing down with? 2, right? That makes intuitive sense. If you have a collection of gases and they're pushing down, the pressures that they exert should be additive. Let's write that in a more numerical way. So we're going to have our pressure total is equal to, let's call it pressure 1 plus pressure 2 plus pressure 3 plus pressure 4 plus pressure 5. You get the point. What can this be expressed by? Or what mathematical operator can it be expressed by? A sum, right? Where we have a Riemann sum. With an index of I, we're going to have P sub I, where I is just the number of species that we have. So this will be pressure of species I, and this is the number of species. So the different types of gases that we have. So that's fine. That will be known as the partial pressure of the species, each of those P sub i's. So how do we figure out P sub I? Well, we do it through something called a mole fraction. So, in order to get the partial pressure, the partial pressure of component I we have to utilize the following equation, where P sub I is equal to chi sub I times P total. So this is our total pressure yet again. What the heck's this thing? That's the mole fraction. So, where this chi sub I is the mole fraction. What's the mole fraction? What it is you take your individual number of moles of species I and you divide them by the total number of moles of all the system. So each individual species, you figure out how many moles you have, you add them up. All right, let's go over a quick example of this. Then we'll quickly talk about real gases, and then you'll be free at last. How many people have classes after this? Okay, never mind. Sorry. But at least you got to be graced by my charming presence today. All right, so what we have, we're going to have the following example. A mixture of gas contains 2.31 moles of neon, 1.01 moles of argon, and 3.44 moles xenon. That is my favorite element. It sounds like a demon name.
Isn't that the princess wizard?
What is from Princess Bride, did you say?
No, Xenon and princess.
Oh, no, that's Xena, the warrior princess. I mean, I don't know. I had friends in high school. I don't know. So what we're going to have, we're going to calculate the partial pressure of each gas. If the total pressure is 3.55 atm at 32 degrees Celsius. All right. So what's the problem asking us? Or what are we looking for? Looking for partial pressures, right? Of each individual gas. How many gases do we have in the system? Three. What are they?
Neon, argon, and xenon.
So we have the pressure of neon, pressure of argon, pressure of xenon. All of these elements are located in the very last group on the periodic table. What's their name, or what's their common name? Noble gases. Why are they called noble?
Because they don't react.
They don't react with the common folk, right? Since they don't react, that's why we're putting them together. Chances are they'll behave a lot better that way. If you have gases that are other ones on the periodic table, chances are they'll react with one another. So a lot of times they place these noble gases together, just so they don't react. All right, so the partial pressure of neon is going to be equal to what? That funny symbol. What's that funny symbol? Well, I mean, what's it mean, though? It means mole fraction. So times the pressure total. We need the mole fraction of argon times P total. We also need the mole fraction of xenon times P total. However, we don't have these mole fractions yet. We do have the total pressure, but we do not have the mole fractions. So let's calculate these. How many moles of xenon do we have? Or excuse me, neon. Let's start with neon. About 2.31 moles. The total number of moles we have is 2.31. which is our moles of xenon, 1.01, which is argon, and I missaid that. 3.44 was for xenon. When you calculate that all the way through, I get 0.342. What are the units on that? Nothing. You have moles up top and you have moles on the bottom. There are no units in terms of a mole fraction. Okay. Let's do the same thing for argon. 1.01 moles over that sum, 01 plus 3.44 moles. When you manipulate that out, I end up getting 0.149. Again, no units there. Let's look at the mole fraction of xenon. Bless you. What value is going to go up top? 3.44 moles. In the bottom, we're just going to have our sum again. 44. When you manipulate that out, I get about 5.09. Okay, now we have these values. All we have to do is plug in and solve. So we have 0.342 times, what was our total volume? Or total pressure, excuse me?
3.55.
3.55 ATM. Why did I put that 32 degrees Celsius there? To confuse you. That's the whole point of exactly what I did. I'll do sinister things like that on an exam. People will throw a bunch of useless information at you throughout a day. You have to be able to tease out what's useful and what's not. When you multiply that through, what I end up getting is an answer of 1.21 ATM. So worst time ever. All right. In the case of argon, 0.49 times our 3.55 ATM. When you multiply that all the way through, what you result in is about half of an atmosphere, 5.29 ATM. For the last one, xenon, we have 0.509 times our 3.55 ATM. When you multiply that all the way through, I get a value of 1.81 ATM. Now there's a way to check yourself with these problems. If you sum all of these partial pressures up, what should they equal? Yes, should equal the total pressure. If you add up all of the mole fractions, what should you get as an answer? 1. Uno. Should get 1. All right. With the time that we have left, we're going to discuss real gases very quickly, or real gas of equation of state. So we talked about when the ideal gas law is best behaved, right? When did we say that was? Under what type of conditions? Low pressure, high temperature, right? Well, unfortunately, some gases deviate heavily from ideal conditions. So what we've done to circumvent that is to modify our equation of state, try and better predict the real behavior of gases. So, real gases. And if we think back to the assumptions that we made with the kinetic theory of gases, what did we say one of them was that wasn't true? Do you remember? What about the space that molecules occupy? They don't occupy space. Is that true? No, that's not true. That's completely factual. Everything must take up space that has some sort of mass. So gas particles occupy space. All right? Gas particles, we said, do not have any interactions with one another. That's not true. They do interact with one another. Even the noble gases do through something called the van der Waals interactions. So those little quotes just mean the same word. Interact with one another. And then we made one more very broad hand-waving argument about gas particles and their collisions. What did we say about their collisions? They were elastic, meaning no energy was transferred. That's not true at all, right? There's no way that can be true. So, they do not have elastic interactions. And all of these lead to a deviation from ideal gas behavior. What we'll do is we're going to discuss one of the equations of state that they've come up with to try and combat this, and then I'll take any questions. All right. So this equation that we're going to put up on the board is known as the van der Waals equation. And what it does is it attempts to try and counteract that ideal gas behavior. Many of you are engineers and you'll probably deal with varying equations of state beyond just the ideal gas law, including the van der Waals equation and the virial equation. So, the way it looks is the following. The minus NB is equal to nRT. And what these A and B's are, A and B depend on the chemical behavior of the gas. So let's look at these additional terms. What do you think that guy accounts for? That A times n squared divided by V. What's that trying to combat? I mean, it is related to that. It has to deal with the pressure. So as you increase the pressure, what happens to the molecules? They get closer together, meaning they interact more. What this tries to combat is it tries to account for interactions between molecules. Between molecules. This NB term that's related to the volume, what do you think that accounts for? It accounts for something. What's the first one that we talked about? Talk about occupying space. What it accounts for is the gas particles actually take up some space, right? It tries to account for the space that those molecules actually take up. Counts for space occupied by molecules, by particles. All right, so we're done with chapter 4. Next time we're going to talk about thermochemistry and the energy of chemistry. Are there any questions about what we talked about today? No, it's for your own personal knowledge. Many of you are engineers and you'll run into different equations of states. I wanted to give you a preload to what you might see. Are there any other questions? Everybody's dying to run away. All right, see you guys next time.